Hello, everybody. My name is Kevin Kocek. I'm the founder and CEO of Chemical Q Device. This is seminar 122, Thursday, February 15th, 2024, for Surpassing the Competition with 3 Quantum-Inspired Algorithm Frameworks. Basically, this is dequantized algorithms, tensor networks, and simulating a quantum circuit. So basically, in all this stuff, when you get a new technology and there's existing technologies in computing and there's just not pure information about the fields, I find it useful to break this into the terms that really matter. So we're talking practical technology that's concerned with the actual doing of something rather than theory and ideas, right? So we can use quantum-inspired methods for sure. Something that's feasible, meaning that it's possible to easily do or conveniently do, efficient, achieving maximum productivity with minimum wasted effort or expense, economical, giving good value or service in relation to the amount of money, time, or effort spent. So it could, also be time economy, not just money. So when we think of these things and you think about quantum-inspired machine learning, we already knew that it's good for sensitive data. And that's a huge thing in medical. You can't have any type of quantum noise or decoherence. Now, what's coming around, especially in these first couple papers in 2024, is performance, right? So we're seeing speed ups, we're seeing scalability, in the sense of how, basically how successfully was it performed and how much does it increase speed? And this could be versus other classical algorithms or a quantum algorithm in theory if it ran correctly on a quantum computer. So scalability, we're usually talking about qubits or quantum bits, but it could also be measured in a range of capabilities. Okay. And then benefit, basically you'll hear an FDA, is it safe and effective? Is it give an advantage of profit gained from something? And is it protected from or not exposed to danger or risk, not likely to be harmed or lost? So you have to think in all these things. Is the inherent nature of the computing method, does it operate in a similar way that we're already getting, say the FDA over 600-700 of those algorithms approved for AI or ML? And then effective, successful in producing a desired or intended result. So the first paper I'm going over, and this is based off of, so the biggest one in this area I reviewed last week is this. It's a dissertation by Ewan Tang, and this one builds on this. I would definitely read their dissertation too, but this is kind of the most up-to-date one, this 2024. So we're talking about dequantized algorithms. So what's the whole purpose of this? And like I said, it's very challenging to take a quantum algorithm and get a complete accurate representation by time or time complexity to use it on a classical computer, but we can get it close enough, they say within polynomial speed, that there's no exponential reason to use it on a quantum computer, which has other associated costs, especially if you were using classical data. And then, just the machines themselves, they're not efficient yet. They take energy to cool, these types of things. So there's a lot of benefit, and the QSVT in specific, quantum singular value transformation by Wiebe et al., is what they call a grand unification of these algorithms. So in specific with the, this MIT Washington paper, it's further improving on the classical version of the QSVT. In other words, it's the SVT. So how this looks is basically, the problem is, in the hardware itself. So like I said, you can sketch down these algorithms, that's the term in mathematics, to, get closer and closer and closer to the quantum algorithm. But there's so many things working against it, and especially for machine learning, right? To the point where it's, not going to be practical for many, many years. So we look at this, feasible dequantized QSVT, i.e. it's an SVT algorithm now. And, it runs at some polynomial overhead, which is acceptable across the field. And the paper is focusing on this SVT algorithm and further improving it from Chia et al. And you also see the original authors of this QSVT. The quantum algorithm itself was 2019. And the reason why it's so important is because it's used for all major types of quantum speedup. So you'll hear QSVT or SVT. Now, the SVT itself, can open up, other applications in machine learning itself that are typically, recommendation systems. There's, several of them that stem from this QSVT or now SVT framework if you're using things classically. And there's quirks to it. So it's basically if you have the algorithms can't a quantum algorithm can resist dequantization with high degree sparsity. So that's a key. So if you're sparsity vectors, these types of things, there's not a classical algorithm to remove that exponential speed up. But in many cases, that's what we're finding is that, so here it is, quantum inspired regression, recommendation systems, and Hamiltonian simulation with this. So for those of you just joining, so this is basically a dequantized paper here. It's cutting edge. It's the kind of thing that you might have to know a little bit about math, but you should be able to, when you read this, these 50-page papers, pull out enough. So what had happened in the previous works with Tang et al., so this is the CGLLTW22, is this specific time complexity. Now, with the numerator, you want to get smaller. So that's highlighted in red. And I believe, if my calculus serves me right, that the denominator, you would want to get bigger. But if there's more of an advantage in this last one, working down, using the polynomial structure, tightening Clenshaw stability analysis, sparsifying matrices, you'll see that the best one, I believe, is at the bottom here. So, like I said, this is an active area of research, and it's what brought all of this together is this survey by Hoyne et al., late 2023, and it brought together dequantized algorithms, tensor networks, and these variational quantum algorithms under the umbrella of quantum-inspired machine learning. Now, their terminology goes well with quantum-inspired is what they're using right here. And, so they say in multiple times of the paper, here's an example of one-on-one, better balance on quantum classical gap than the 2 regression papers, 2 recommendation systems papers, and a Hamiltonian simulation study with improved dependence in each relevant parameter, meaning the A and the epsilon, on the previous slide. So why this is important for not only quantum-inspired machine learning, but opening up new applications in machine learning is we now have, rough approximations of the quantum algorithms, but running them more conveniently, cheaper. There's way less issues with the hardware with classically to really start advancing this field at a very fast rate, in my opinion. So the way that this is done is you'll read in this paper, so Clenshaw recurrence as an iterative method for computing matrix polynomials with sketching techniques, and they mentioned that too, to simulate QSVT classically, and then followed by these 3 steps. So you'll see Clenshaw, Chebyshev, these are other people that have impacted the field quite well in linear algebra, basically. So basically, if you go at this head-on approach, you're going to experience error. So they add error at a specific step, and it can be referred to in classical terms because many of these papers that have been built upon to get this far with these SVT algorithms in the paper are based on previous linear algebra techniques. So error accumulation, these types of things. So the take home in this paper and the next paper I'll be getting to is approximations are needed because if you go to run quantum circuits, you run into the RAM issue with quantum bits and these types of things. And it's the same thing with dequantizing algorithms, is that you're doing things a little bit different at different steps in order for the end time complexity to be as close as it can get to the quantum algorithms. So there's other approaches with this too, and it draws upon randomized numerical linear algebra from previous papers here too. And you'll see this, in the process of algorithms trying to never produce a value that's much larger than the final value. Okay, so the take home with this paper is it's a process, right? And there's steps that might not make sense, but they're there in order for the end algorithm to have a better time complexity. Now, there's still quantum algorithms out there that may have a large polynomial speedup. It's looking far and far less for exponential speedup, which would be a big reason to run a quantum computer if it didn't have, noise or decoherence. But Zhao, Fitzsimmons, and I think it was Fitzsimmons on their own, a Gaussian process regression in 2019 that's still believed to have some potential for large polynomial speedups. And then so Seth Lloyd et al. Here, Gardnerone and Zanardi with topological data. So these two, Gaussian process and topological data, if it ever came to a point, like I said, this is less for, machine learning because it's really hard for quantum computers to fix all these problems. But more in the future, if it did reach the point of being able to do that. Are there any questions regarding the dequantized algorithm paper? So by Tang and, the other MIT researcher. And feel free, so you could put comments or ask questions in the chat there too. Now, the reason behind all of this is that tensor networks are a little bit off on their own compared to, the dequantized, using the term quantum inspired, less. But essentially, in this specific paper, there's an IBM quantum processor that uses the heavy hexagon lattice, and this was done to help try to improve the quantum computer. Now, if somebody wanted to run this on the quantum computer, it doesn't run, terrifically. There's noise, and you can see the noise bars that I'll show you. But if you use a tensor network simulation, even though it's an approximation of the quantum circuit, but it's done in an effective way classically, on CPUs or GPUs, and it actually didn't take too much, like a single cluster to do this one, is, that makes up for all these other issues that the quantum processor has by using an approximate or a compressed method, such as tensor networks. So the reason why people want to use tensor networks is to reach higher qubits. And the authors, basically their belief propagation tensor network is to kind of fix these issues with the expense of quantum computers, inaccuracy and inefficiencies to run. And the tensor networks themselves they found perform a classical simulation that is significantly more accurate and precise than the results obtained from the quantum processor and many other classical methods. Now, the classical methods in this case means the other tensor networks that came before this paper. And some, I believe, use belief propagation, but that's kind of the crux behind it. And its quirk is you can't measure error directly. You kind of have to use, it's called an MPS tensor network to assist with that. So this is effective, for scaling this up. And this is still not a huge problem. This is run on a quantum computer. And to be used for many body dynamics, that's synonymous with particle physics or different areas of physics that are less familiar with the quantum inspired kind of movement going on. And also there's limitations to it, is that if it gets into this loop type network that's not tree like, then it could also accelerate some of the error related to it. But by and large, when they ran these experiments, and I'll show you some of the graphs or the charts coming up here, is they found that performing these simulations to long times in the thermodynamic limit corresponded to a quantum computer with an infinite number of qubits, okay? So what this means is basically the approximation of the tensor network is good enough, and that it doesn't have to be anything that's perfect. Like a state vector algorithm, when you go to run in a quantum computer, it's run without approximations, it's run exactly. But, say for instance, dequantizing methods and this other efficient method for tensor networks is it's using, these types of, approximations to even get to the point that we can't get to, if we want thousands of qubits, and this is saying an infinite number of qubits. So what makes this practical, and effective is that it can be formally computed in polynomial time on a classical computer. So when people are adjusting and making these, tensor networks, all of this is, in the back of their head as far as, what, is going to work, being scaled up to more qubits. So we see the 127 qubits left, and this is actually on quantum hardware. And you see what it looks like on the right. So, these are the individual, so this is the tensor network, and a tensor network is needed to simulate what was done on the quantum computer as a proof of concept to make the comparison. And this is the gist of the paper. So basically, belief propagation, which is they use this a lot, also known as sum product message passing. It's used by authors for performing inference, such as Bayesian networks and Markov random fields, and these are quite common, in machine learning. And like I said before, the downside to this is there's currently not a benchmark for belief propagation, what they use. So they use MPS and other methods to confirm the results that they're highly accurate and tree-like. If it's moving from this tree-like structure, then it means that it's not doing, it's more in a loops, so it's not as effective or accurate. And there's quirks to it, right? So you can't do everything in tensor networks. There's things, and the research keeps getting better and better. Like I said, the thing with this one is the accuracy in going to an infinite number of qubits for a specific configuration of tensor networks. So here's the other thing, scalable. So they say as the number of heavy hexagons increases, the belief propagation approximation improves significantly. Okay. So these are the types of minor details in papers that can make a huge impact. Now, the way the field wants to move is mean field theory. I believe that wasn't the goal of this paper. Is more to just show using classical simulation we could do things better. Now, okay, so the takeaway with this specific one is basically the circles are the quantum processor, and you can see the error bars are quite large. Okay, so we're focusing on A, or the left diagram here. And what happens is if you use just an MPS network, so this is like the simplest tensor network out there, it's basically, for these number of steps, it does not fit the exact curve. So the exact curve is this dash line. So this dash line is what's desired. And you can see the quantum processor is not that far off, but the error with it is so high. And the one that works the best is their tensor network simulation with belief propagation, this at x equals to 500, and the blue almost overlaps the dash line exactly. So the reason why people were talking about this in news is because these are the types of results that people want. And again, to go the direct route using a quantum computer with a host of other, hardware issues and, cost and, cooling the whole thing down, we could see where it's at this specific case. Now, what was done here on the right is it says it's a weight one observable. So what's to be noticed here is the quantum processor, does still have these error bars, and it looks like the scales are the same. They're just condensing this one on the left. But anyways, there are conditions that a quantum processor can run better at. But out of everything here, it tended to be this belief propagation. Now, two other tensor networks, this ISO-TNS and red, did not perform well. They performed worse than the quantum processor. And then the orange one, which goes back to the MPS, also did not perform well, although they don't have these error bars associated with the running on QPUs. And then the tensor network with belief propagation performed the best here, and especially without error bars. Are there any questions at this point? So we're talking about tensor networks, and we're talking about, approximating, instead of running state vector algorithms exactly, they're very efficient methods to get the qubits up. And this is for, different types of quantum systems that are known to be in nature. Now, this one, actually, I don't think that they have an exact. So some of these, it just depends on what's available to measure. But this places everything, you can rule out. So let's start with the Eagle processor, is that it's not too far off from the curve. And again, it's run natively. It's not, it's approximate, these types of things. But you kind of see where that lies, especially with the error bars, every time you see the hollow dot. MPS, ISO, TNS, orange and pink, and then the TNS at these lower values x does not do as well as going to infinity. And again, we see this dash blue line, being what looks to be the best case out of all of these. And that was similar to the previous slide. So how do we do this? Is I've been looking for tensor network Python notebooks, and I think they get a little bit more into like, there's these terms called gauging, contracting, partitioning, evolving, that Julia is the one to use in this specific case. And I think I ran into other .jls or Julias, to look at this. So you need a good problem, or you need to have something like, this original Eagle processor. I think they have the file up, so then they can compare to that. And there was a slight misunderstanding with some of this. Is basically they used a single node on their Rusty computing cluster, so you can look into that. So this is more getting into like maybe mid-scale kind of enterprise computing is what that looks like. Now the MacBook Pro 1, which they mentioned in the paper, was just for timings and memory usage and not the collection of data. Okay, so they said it, this isn't an efficient process in that it's only using a single node, but it comes down to, how fine-tuned you want to do things as far as this term called gauging, how often you want to do things. So there was another interesting paper in 2023 with this, dissipative mean field theory, which many people are after, to simulate this system. But it did not obtain, it obtained relatively accurate results, and they said not quite as good as theirs. So there's a number of different techniques in tensor networks to use. And like I said, it's the one that gives you the performance. It's efficient. I don't know as far as like doing really cool problems, maybe on a really top end MacBook Pro. I'm not quite sure, but it's not running the state vector algorithm. Okay, so it's an approximation, whereas dequantized algorithms is taking quantum algorithm and then approximating it into classical, just so we can just use this a ton over and over and over again. So it's kind of less of this theory into like, if we only had a specific computer, and it's more today, and we can actually run these, and we can get benefits and different utilities based on these three papers alone. And where this is all leading to is basically, this is for the win, right? So there's enough in industry, people switching to quantum inspired with, GPUs and quantum algorithms. And we see it especially in academia. And I'll kind of be subbing that too. Are there any questions regarding tensor networks? So this other paper is basically a shocker, right? So this came out, I think, 2 weeks ago, and I reported on it last week. But basically what's going on in quantum hardware is there's a technology called neutral atoms, and this specific one was QEra with Harvard researchers. And IBM and IonQ ran this simulation just to show that, number one, they could beat it noise-free a lot faster, 100 times faster than QEra, and then also scale it up 2x to the original, and then scale it up again 4x to the original 48-qubit circuit. And they call this IQP circuit. It's a more challenging compared to like a standard embedding algorithm, a white box computation. So meaning that we can see kind of what's going on inside of it instead of black box, and you hear black box all the time. Okay, so the problem is, and this is kind of being highlighted, is quantum circuit studies are expensive to run, have quantum noise, and lack speed. The actual Harvard QEra to run this is their time comparison is this 0.3 seconds, but to do post-selection and partial error correction is actually 3 days. Okay, so the value of this 100x is the 0.3 divided by 0.00258 to get approximately 100 times faster. And keep in mind, all these simulations are without noise. So it's not even a direct comparison to compare to the quantum computer, because even after it, spent additional days, with the processing, with error correction, you're still not talking the, a one-to-one comparison. So the moral of the story in all these papers is just this, is like, there's lots of things in theory, right? There's things in theory that two and a half years ago when I started my startup, I believed in. And these 2.5 years have passed. And over the course of this time, I was introduced to quantum inspired machine learning. And this is a practical technology. So even if the algorithm, a dequantized algorithm, is not quite as fast, it's practical. Yeah, so we can use this over and over and over again. We could use it, run it all night long. CPUs, GPUs, TPUs are readily available. Okay, so like it alluded to before, so the 48 qubit circuit that they simulated compared to the neutral atom quantum computer, much faster, 3 orders or 2 orders of magnitude without noise. So I call it noise-free simulation supremacy, right? Because that's pretty clear. Now, the 96 qubit was not slow, so 4.2 seconds. And this is on a decent Google Cloud, 224 gigs, 112 virtual CPUs. It's a rental. I think it's like $4 an hour. So a comparison with this to run this 96 qubit at 4 seconds is a A100 GPU is about $1.30 on Colab. So, you could do awesome stuff with CPUs. And actually for the 192 qubits, they use mostly TPUs. So that might be another benefit in, processing, is not just to use GPUs or CPUs. But for this specific case, it's part of the Clifford circuit, this harder part of the quantum algorithm. It just does better on TPUs, apparently. So anyways, this is available compute. And like I said, if you sign up for Google Cloud, and you can get the rates maybe down by half if you don't want to run on demand, if you're not quite sure. But basically, IBM Quantum and IonQ will likely continue quantum computers, right? There's many other applications besides machine learning that could be a sweet spot for quantum hardware that's tolerant to noise. But to get an advantage, a true advantage, it probably has to do quantum data, which is not synonymous with what's practical today, but it could be something in the future. So the other part of this is the CNOT gates. So if you've ever tried the Penny Lane or Qiskit demos and you try running CNOT gates, and I'll show you in the next slide too, they don't like simulators, right? But in this specific case, and you'll see the IQP circuit, and they took out the Hadamard layers in the beginning, so vertical, and at the end, so you see all these CNOT gates, okay? And this one on the right is basically runtimes in seconds. So this gives you an idea of the slowdown from 48 to 96. Now, as far as I know, in literature, 62 was the highest ever before. And this 96 qubit circuit at calculating a single amplitude was achieved in 4 seconds, roughly. And we see adding CNOT gates, they actually did not seem to increase runtime at all. So if you're not familiar, so the width of the circuit is associated with qubits, and the depth of the circuit would be adding more CNOT gates, left to right. So this is basically, I believe, so it's saying 96 qubits fixed and then adding 5 additional CNOTs. And this is not the trend that people have been seeing. So I'll give you a little hint at what they did in processing on the next slide. And, so basically, these methods are still worlds apart. It's good to see it on quantum hardware, as far as something in the future, but there's differentiation methods that are issues with machine learning and quantum hardware. So these would probably be a single big problem that a quantum computer can do in the future. So we see this 192 qubit circuit that was done on significant compute, like training a deep learning neural network, which is on the processing end of things, a lot more complex than a single quantum circuit typically. But it took about 4 days to get to 192. And this has blown any other kind of projection as far as a single state vector circuit running at more than like 50 or 60 qubits was thought not to even be possible. And then now they say the new benchmark is 384, error corrected on a quantum computer. And I guess to all those out there listening is, based on all this literature, the only hope that quantum computers have is with quantum data. So quantum computers process quantum data best, and classical computers process classical data best. Now, what we're doing in quantum-inspired machine learning is taking quantum information, either removing it or portraying it through quantum states to process the classical data, right? So the benefit, and I see from this paper, as I dig more into these papers, the 96 qubit quantum circuit will likely motivate quantum inspired machine learning even more, which costed less than a cent in around 5 seconds. And this is without all the other machine learning processes, but it's a lot easier to make comparisons between algorithms, quantum inspired algorithms. Once you get into machine learning, you're introducing many other variables. So here's what I was talking about. So the teal on the top here is basically this Bluffstein et al. And then the bottom one is the IBM Quantum and IonQ researchers. Now, the exact reason why they ran this experiment is probably just to slow down neutral atom, as it appears to be getting advantage and, like, again, a lesson AI kind of ML stuff, but also buys them time. So they probably have something up their sleeve running on an ion trap processor coming our way, maybe even that 384 qubit circuit. It's going to have some noise. It's going to not be able to run continuously, but it would advance, quantum hardware. Now, on the right here is basically we see, and I believe, so this is not typically available on gate-based superconducting qubits, which is IBM. So this is more something you see like ion trap. And apparently it's the single CNOT gate. It says constructed by combining transversal and permutation CNOT gates. Okay, so it's a software technique, right? They're running it on classical hardware, and what they're basically saying is you can actually use CNOT gates. Now, the thing about state vector algorithms is there's no limit on entanglement, whereas with tensor networks, you're more talking limited entanglement. So in certain quantum systems, there's just a limitation currently on the tensor networks. Now, the issue that state vector has is it goes exponential in RAM pretty fast, but to get to the 192 qubits is very significant. So, and again, these are, free of any type of quantum noise, these types of things, and kind of like breaking the mold of what we put all of this in. Now, are there any questions at this point? So we'll go on to the final slide after this. So what I just covered is the dequantized algorithms, single value transformation is better, keeps getting better, which is the comparison for QSVT, but this can be run on classical hardware. This field has a lot of potential. Tensor network simulations, you see a lot of people wanted to run some type of physics experiment on this, and we saw the direct comparison to what was done on quantum hardware versus what was done on simulators or classical hardware. Now, the last one kind of shocked a lot of us. So it beats the Q-era, or IonQ and IBM beat the Q-era Harvard 48 qubit circuit, not only in noise, and then they scaled it up to double, so to the 96, and then scaled it up to 192, which is 4 times the original circuit. And again, without any type of quantum noise. So, again, I think all of this kind of goes into practicality. And like I said, with my limited 2.5 years, solely focusing on quantum, for medical, is that, it's becoming pretty clear that this rate of change, for quantum hardware was not nearly what I thought it would be based on reading industry reports. And the more I stuck closer to academic papers, you can, get a lot more information. So where does this put everything? So I'm using the term for the win is for quantum inspired machine learning in specific to the 2024 these papers, three papers have strengthened the technology for AI industry growth. Now, for the win is basically describing a play that results in a win, bringing the game to a conclusion. Now, the conclusion here is for artificial intelligence and for machine learning that it's going to be with quantum inspired methods, right? There's just, and I've done reports and all these other kind of software guides to look in, but that's just how it is. Now, it will be the primary quantum computing method to improve AI for many years, so this is a specific type of quantum computing. And as far as it being performance and scalable, the adoption of Kimmel and the ease of use of it and the practicality and no noise will outpace other quantum computers, especially for AI. Now, like I said before, quantum computers will remain viable for processing quantum data because those can't be dequantized, only if you're using classical data, which everybody uses today. And they're resilient to quantum noise, decoherence, and so less of AI anyway. So, but specific cases for big problems, but probably not the machine learning workflows. And the big thing is that Kimmel was already known to be safe for it doesn't have any type of quantum noise. But the key with this has been the performance and the scalability. We see in the accuracy of the tensor network, we see the speed ups, continual speed ups with these dequantized algorithms that are run easily on classical hardware. And more and more qubits going up to infinite in an approximation. So the benefit is basically these dequantized algorithms, tensor networks, and quantum algorithm results have become very significant, as illustrated by Yu and Tang, and then this point et al. This survey that if you were to start anywhere besides my work, I would start there too. It's this 2023 September point et al. And it goes just like how I'm going through dequantized algorithms, tensor networks, quantum variational algorithms. And on top of that, the industry has already adopted to using GPUs with quantum algorithms. So this all falls under quantum inspired as well. So we're talking NVIDIA, we're talking Classic, we're talking Terra Quantum AG, Google Bard, and a whole host of others. Sandbox AQ working with Sanofi, and Johnson Johnson with StrangeWorks, many. So what's included here is basically this transition, bringing the game to a conclusion that we're using this technology into the future. So for medical school research, it's a safe technology. It uses the same hardware as what they're using for deep learning right now. And, there's all these, software migration guides, the seminars, all this type of stuff, and being appreciably better than the rest of the field. And so we're either typically talking versus quantum computers or existing classical algorithms that came before that, the new paper. So are there any questions at this point? And, feel free to put in the chat. But once you grasp what's fully going on here, and there's many papers and literature that are using medical data, with state vector algorithms. And we all know the issues with, you could get better performance, but can you run classically with that extra time that you did? And these papers, especially the dequantized algorithm paper, and tensor networks too, are these kind of like useful, practical, methods, as opposed to insisting that we have to run a full, state vector algorithm exactly, but we're reaching our RAM capacity relatively soon. So same thing with tensor networks too, is that's what that aims to do, is efficiency. And, getting to that point is more important than doing it properly. I hope that makes sense. And where properly in this case means the exact state vector algorithm, or say doing it exactly on a quantum computer because it's native to that. So that's how I would sum all this up. Is basically getting to that solution, as opposed to doing things the most traditional way that have proven over and over again not to produce results or be too RAM intensive. Any questions regarding any of the slides? So here's the references here. And then, so, at this point, there is no debate, for AI and machine learning as far as using this type of quantum computing method. This is the way to go. And, like I said, if you want to be in the industry for a long time, and especially with machine learning, which is like number one stuff anyway, why not use the quantum computing method that has been now showing great results, scalable, works, these types of things. So yeah, it's looking very good. I saw a couple of people kind of come on here. So Dino, Edwidge, or Samuel, any questions regarding slides? Go ahead.
No, no questions, doctor.
Yeah. So, the key with all this is just the research. There's only so much you can get from industry reports. Even if Sandbox AQ is saying they're using tensor networks with GPUs, fantastic. But that came from some paper. And that was before this big one, the number two paper here on tensor networks. And as far as anything else here, so as far as researchers to follow, definitely follow Ewan Tang. So she was her dissertation, which I included in this list on the slide after this, is called Quantum Machine Learning Without Quantum. But what it means is using quantum algorithms, taking out the quantum, turning them into classical in a way that we've never conceptualized algorithms before. So that's what dequantized means. And Flatiron and NYU, and I've seen other developments from NYU more on the lecture side. And IBM IonQ is synonymous with IBM being the gate-based superconducting qubit, IonQ for ion trap. And again, this specific paper is shocking, but it also doesn't rule out their future developments. It just buys them time, just saying that a classical computer can still do way better than the neutral atom computer. So again, the number of algorithms that have been dequantized is like at least 8. And this is basically saying there's not a huge significant reason to run these other principal component analysis or recommendation systems and support vector machines on a quantum computer. Now, keep an eye out in the news and in literature, because yes, you can always get better results, but it all comes down to how much time it took to get to that. And it's good that we're at this point to realize, if you're not using an efficient algorithm, that there's very likely some other classical method that can beat it. And I've had these too. I've had a lot of research where I get that performance. Now, if I go back, I probably have to implement, some of these methods. So it's just part of the process. And I took parallel quantum algorithms further, and it makes sense to run a limited number of parallel algorithms, like state vector algorithms, because you're running more quantum algorithm and less of the machine learning process, right? So that's another avenue there too that's under quantum inspired. And as far as all of this is that be very careful, because I remember hearing this as far as like you'll never be able to simulate a quantum circuit over 50 qubits or 60 qubits, and then here using software approaches and finding equivalencies in entangling gates or CNOT gates, that very thing is being done. And they always said, CNOTs, you're always going to go exponential in time, adding additional CNOT layers. And like I said, using their software approach and turning all this, basically into running very efficiently on classical hardware, it is the way to go, especially for AI and machine learning. And let's see. So, as far as where to go next, with your own research, because we get people, or that come on to this discussion and they say, we just want to use the best, or we don't care how long it runs. Well, that's probably not the best approach, because like I said, there's going to be a classical method that is going to be faster, right? But now with dequantized algorithms, this approximation method of the quantum algorithm, this is looking like a really good algorithm to run, either to replace existing applications and or new utilities, and quantum inspired regression, recommendation systems, stuff like these. So, it's hard, but that's the key, right? Is to stick with literature. It's very dense. There's they'll typically tell you everything, as opposed to I don't even read these reports. There's a report that reported on this, and a lot of times they're not completely accurate, and a lot of times they're very brief. So, but something like scalability or something like that for the tensor networks or accuracy, it'll include that. But that's the key, is to refer back to the original literature. So with this specific one, when we see these error bars kind of getting better, it looks like it's hard to tell because of the scale, but they say they're both 0 to pi/2. There are experiments that you can run, with quantum computers that would make things better. And, if we're talking about small tensor network simulation of this, IBM icing kicking circuit, it's just, you have to keep all these in mind, but you're just going to always have that noise around, especially this is the Eagle processor, which is 127. I think they tried to release an Osprey at 433, but that's not the issue, because INQ, I think, is sticking to like 20 something. And now with these experiments going up to 192 on classical hardware, then where does that put the INQ? So these are all things to think about, but I think it's pretty overwhelming now across these three disciplines: dequantized algorithms, tensor networks, and variational quantum algorithms, that there is a simulation advantage, a noise-free simulation advantage, as opposed to running other methods. So, it's important because there's a lot of, say, for instance, the next big quantum hardware announcement will say XYZ, and they always say one thing, like it's still in infancy, but that's pretty much all you get. You're not going to hear over and over again about, it's to the noise of many orders of magnitude more than a classical hardware, or decoherence, these gate times being, still relatively, not long or not good. So, yeah, and I saw at least one other person hop on here. And, if there's, basically this is the direction for machine learning in the future using this computing method, which is just plain old CPUs, GPUs, or TPUs. And, with the performance now that we have with these papers, and going to being able to scale to infinite number of qubits accurately, as opposed to running things natively, but they just don't run well. That's that, and combined to the pace of innovation that we have now, classically, with, NLP and chat GPT, and, things are moving very fast. The new NVIDIA H200, 76% more RAM. So calculate that into the configurations. And then we'll see kind of the RAM bumps, probably whatever it's, an A200 or showing up in your Colab or Google Cloud. But feel free to put anything in the chat. And again, I'll have this up, pretty soon here. And like I said, it's nothing to, you have to be aware of these things, because like in industry, you can get off, just running something that's just, okay, we got better performance, let's just go with it. And obviously somebody like a deep learning.ai that is also academic, that helps out industry, they can say, okay, well, you could do that, but you could also use some other method on top of that. And then, kind of nullifies your whole reason of claiming your advantage, right? So I think this is what the papers do in specific, this Tang et al., the specific one, is we see the D numbers go down from 22 to 11. And, the 6 goes down in this matrix A, go from 6 to 4. And let's see, I take that as a divide sign, but this epsilon, I'm not quite sure about. Because typically when you go to divide by something, you want that to be bigger. But anyways, their progress is marked by here in sparsifying matrices, which is this whole process of using linear algebra from the past and pulling up old papers and using those methods, and to get to the best answer. So again, that's not always the most direct, is the direct method that other people are using does not always give you the best solution. So in summary of these three, and basically all this other stuff too, and what's really important in any technology is to keep an eye on all these terms, because with quantum inspired machine learning, there's papers out that satisfy many of these in a single paper: practical, feasible, efficient, economical, high performance, speed up, scalable. These are all the terms that I talked all throughout the lecture: benefit, safe, effective, these types of things. So there's just a lot of different angles that people are coming from with this, with their hopes and expectations of a certain method or computing method working, that it just isn't going to work for AI, right? So there's differentiation that is efficient with quantum inspired machine learning. You can either use back propagation or adjoint differentiation. That's not available on hardware. And those other cases go exponential in input size. So more and more inputs, more and more time, that kind of thing. And, these things just stack up. But, a lot of people come at from different perspectives. So somebody in medical regulatory want to see safe and effective. Okay. So effective is also a function of performance. And then, many other people, maybe less, maybe more in the NIH researchers that want to see this get better, they want to use the one that's scalable. Well, I think dequantized algorithms and tensor networks are both very scalable. The quantum algorithm, the INQ IBM paper on the state vector algorithm that's exact, that's more in question, or that's harder, to make the effort that if they go from 192 qubits, can you go up to 300, 400? And again, 50 or 60 was thought to be the limit. So usually the answer is yes. But I think the two methods that have the highest return or ROI at this point is going to be the dequantized algorithms and the tensor networks, just because they allow, with approximations and error, doing these types of things, to get to that point that you want to be at, as opposed to just crashing out with in either runtime or RAM, like a state vector algorithm. But it's the type of thing that could be improved, and our idea of state vector algorithms could change. But there's many quantum circuits out, and there's that's the most popular method by far, is the state vector algorithms. But taking to the next level where they're very practical, the 192 qubit that was on, basically 5,000 CPUs or TPUs, equaling 5,000, that combination of those two. So, that's the easy stuff, right? All this stuff we can run today, assuming you're interpreting it right from the literature, but it's all here and now. So it's like, if somebody were to say, like, what's the primary application for quantum computing? And most, if not if all, would say quantum machine learning, which, is more towards quantum hardware, but that's not practical, and it won't be. And I've highlighted this in guides, like 5, 6 other things where that's just not going to happen. So if the main application for quantum computing is quantum, some form of quantum or some form of machine learning, then most of the resources should go in this direction. And that's just, as simple as jotting things out on a piece of paper, right? If you say, this XYZ company runs nonstop machine learning experiments all throughout the week, nonstop, and they're buying more compute time and over here and over there to reach their, objectives, then it should be the same thing, using some forms of either quantum inspired, like dequantized, or tensor networks or variational algorithms. So that's where the math doesn't make sense, is because the big problems that could be solved by quantum computers haven't been. And if this goes on for several more years, I think a lot more people will be thoroughly disappointed, especially because they can't do artificial intelligence in the form that we see it today, constantly updating, ability to run algorithms whenever you want, practical, these types of things. So I think, its time will come, quantum inspired machine learning, because there's so much money, like billion-dollar IPOs. There's, all these, I think Quantinuum just got $300 million to further advance their hardware technology. But the end goal, I don't think, is equal to this, because this is many, many people running machine learning with, some form of quantum computing over and over and over again. That is a limited number of people accessing an instrument or a computer that's not machine learning, that's likely just a single chunking through a big problem. It could have a great impact, but I think history has shown us that the iterative approach is needed in order to get to the optimal solutions. So that means, like, even if we have that, an ideal quantum computer in 5 years, is that allowable by many, many researchers in order to get to that optimal solution? So these are things, to keep in mind. And, obviously for AI, quantum computing for the win is definitely quantum inspired. Industry, academia, available resources to start using it, more so medical, NIH researchers, FDA, these types of things. And, it's a very exciting time, for the industry. And again, I want to thank it's the Hoyne et al. Researchers the most, because they pulled all this together. Because you'll see in tensor network papers, they're not really aware of dequantized algorithms, I don't think. And they don't use the words inspired, but that whole that whole paper was inspired by an IBM quantum circuit. But this one in specific, this 2023 in September, is a must read. And it's dense all the way through, especially dequantized. Everybody knows about state vector algorithms if you're in quantum computing. It also does a decent job with tensor networks too, but there's just so much upside also with the dequantized as well. So, and this is the practical aspect that we're looking at as far as, we can do this kind of stuff. Are there any questions at this point? And then, so feel free, so you could put in the chat. And, it's the type of thing, at this point, everybody's been sharing lots of stuff with the technology, either in papers or GitHub repositories, these types of things. And I think that you have enough, listening to this to make the informed decision as far as, I love artificial intelligence. I love to do machine learning experiments and go to other machine learning groups. And now you have these other 3 big tools to use. One's coming off of this quantum algorithm that you can run classically, tensor networks, allowing you to do physics simulation that you couldn't before. And, state vector algorithms, qubits keep going higher, but it'll likely need assistance probably from dequantize or something to take it to the next level. But for exponential growth, definitely the first 2, the dequantized and the tensor networks. And there's other types too. They fall under the other category by Hoyne et al. Here. So I think it's, 52, 53 pages, something like that. And the dequantized paper by Ewan is this specific one, Quantum Machine Learning Without Any Quantum. So this is dequantizing algorithms, but it's a very good overview of, she gives a graphic of what they thought could be run on quantum computers, with an exponential speed up. And then after her work, her dissertation work, there's few left. But these ones that have been dequantized can be used for quantum inspired. So, and she uses the quantum inspired, terminology too. Awesome. Anybody else that came on kind of a little bit later? So this is definitely, like I said, we've seen enough. There's a ton of medical images in quantum inspired, machine learning, mostly from quantum transfer learning or others too. And, getting down to the bottom of things as far as, like, now we have an algorithm that's for sure our best classical option, it comes from quantum, you know, as opposed to just saying we just got better performance, but we're not going to talk about runtimes because all of us had that issue. And feel free to put in the chat, as far as different areas, if you're coming more from quantum or if you're coming more from machine learning. So, I'd say it's harder. The bulk of the meat's in the machine learning. And yes, you do have to know, quantum, but it just depends because in tensor networks, there's, a lot of, calculations and adjustments, and you have to know the system very well. Awesome. And anything else? Any other questions? Any other links? And again, I'll have this up, so you could access it. But I think it's a very, promising time, and it's going to be a challenging time for people to adapt, thinking that they could do quantum computers with AI, right? But not directly and not for many years. So Samo says more and more publications on the subject are appearing. Yeah, and it's good to share these too. So if you have anything else with that too, because I'd be interested, because this is my journey too. If you're talking more so dequantized or tensor network or variational quantum algorithms, and is there a speed up, what the performance is, those types of things. But we've already gone through the first, second generation of medical images and quantum inspired with many of these models that I know. So the whole point is to go more scalable, better performance, these types of things. But yeah, it's good to hear that, Samuel, that you're coming across these. And like I said, you can feel free to, post anything you want as far as what you're finding. Google Scholar is very up to date with all this. This is all included pretty well. So if you're looking for a specific area, it picks up dequantized algorithms. But I would say ChatGPT a little bit less on dequantized, and it does okay on tensor networks. So Dino, maybe a little bit more specific. So there's a question in the chat. Any quantum algorithm for HEDIS, HEDIS? Go ahead.
Can you hear me?
Yeah, we can hear you.
Okay. Yeah. Both of them.
So your question was regarding this HEDIS?
Yeah, HEDIS is pronounced he.
Uh-huh. And then could you provide a little bit more information on it?
Yeah, it's set up by NCQA, and what they do is you use HEDIS scores, HEDIS rates, to gauge performance by providers or provider groups. They get incentives if they get certain percentage of say annual visits for the member. Like for instance, right now I'm working with Medicaid members for certain states in the U.S. And usually the state will say, hey, if the providers in your insurance group gets within, say 50% of annual health check visits, we'll give you, we'll give you this much money. It'll be more for 75%, and the higher it goes, so like an incentive for the insurance company and the provider to get their HEDIS rates up. It's all medical data.
Yeah, I mean, I'm trying to think what's kind of similar to that. And it's basically a percentage, a financial percentage based on a variety of factors.
Yeah, yeah. I know in Indiana let's see, what they've done is like they hold that they'll say we're going to give you let's just say pay you, say $1,000, right? We're going to pull back $1,000 if all your providers get within a certain percentage of certain medical measures, like annual welfare visits, breast cancer screening, uh, it's a lot of what do you call it, preventive measures. If they get, if say you have 100 members, and say a provider has 100 members, and they get 50 of those members to get their annual well check visit, so that the rate will be 50%, right, for one provider. But if you get 50 providers in one provider group, then they average that out for the whole group. But each provider will have, again, just make it simple, say 50 providers have 100 members each. That's not realistic, but try and get the percentage easier. So
And then,
they'll
I
get
guess,
higher. Yeah, the higher the rates are, they'll get more incentive in employment.
and I guess
So,
what's the limiting on the compute side? Is it dimensions?
um, so we're trying. What I'm thinking of how to use the quantum algorithms to kind of predict. One example I think I read somewhere is predicting who will, say, miss their appointments, which members will miss their appointments based on past data.
Yeah. Okay, the closest thing I have is so the ex FDA commissioner, he goes on to like all these like squawk boxes, like the financial things, and he's yeah very in favor of using NLP. So in our version, like a Quantinium, Bob Kuka, he uses QNLP to basically take in patient calls and make these more informed decisions where it doesn't necessarily need a doctor at this point, and it's more towards like at this step it's okay to use NLP in medicine, and we might see this later in the year for like an FDA approval, maybe. But that's what it reminds me of. And as far as it sounds like you have a lot of variables, and if this then this, if that then that. Now, out of everything I talked today, the one that rings to the closest bell is, say, if there's an algorithm in there that could run better, like the SVT, which is dequantized from QSVT, which can speed up that process. It's the grand unification of all quantum algorithms. Something like that on a more fundamental level. You might want to check into, because that's what it sounds like the most as far as NLP stuff is, Bob Kuka at COECKE at Quantinium or Oxford Quantum. And that's what they focus on is NLP with quantum. So it's going to be the enabling technologies like the dequantized algorithm or tensor networks that are really efficient, that can take in all of this information and maybe put it into a package of what you're looking for.
Mm-hmm.
But based on all these three, I can't think of anything in specific. And I guess the next step up would be, if this falls but better under the dequantized PCA, or maybe that's better than the classical. And you can go through these papers and kind of see like, okay, this one makes sense for this. So yeah, it's just the power in AI is coming from the number of parameters mostly. And there's an argument as far as stopping at billions or going to trillions. So a chat GPT uses trillions of parameters to use the internet as the training set. So, for these types of things and sheer, going through a transformer model that's, generative pre-trained transformer, chat GPT, that sounds like that's taking in the most and kind of chunking through the most. And I would say the next steps for quantum inspired is to look at all these single algorithms, see which are better in quantum inspired, and that's easy, right? So
right.
Yeah, as far as something like a whole solution to your problem, that might come a little bit later. And then maybe now, as far as like pulling all these papers together and say like, okay, this uses this algorithm here. This just knows to run, polynomially faster with this quantum inspired algorithm.
Yeah. Original in the chat looks like you had a good standard explanation of fetuses.
Yeah. Yeah, so I appreciate that, Samuel. So healthcare effectiveness data and information set, one of the healthcare's most widely used performance improvement. Okay. And more than 227 million people are enrolled in plans that report HEDIS results. Okay. Yeah. So like I said, that's how it is. I'm basically saying this is the discussion is for the win. This is the type of quantum computing method to use to improve, today's AI. Okay, and there's enough behind it between dequantized and tensor networks to justify that. So yes, it'll take some time, to get to a finished product, but if you or anybody else that is good at substituting algorithms, or this one can fit in here, and then you claim your performance on there, that's probably the easiest way to go if you want to stay quantum. You say like, I use quantum inspired.
Right. Okay. Thank you.
Yeah, you're welcome. Any other kind of last questions or comments? I appreciate everybody coming on again. So this will be up on YouTube, and I'll have the discussion up on LinkedIn as well for the slides. The other links, to go through as far as software migration, the Hoyt et al. Paper, the Yu and Tang paper on dequantize, will be up as well. Awesome. If there's not anything else, I wish everybody a good rest of the night and a productive rest of the week. Take care, everybody.